If you just joined, there's a URL at the bottom of the screen. Take a picture of it and then go to that URL so that you can get the slides and the notebooks. And if you haven't already, sign up for a community Databricks account so you can actually import the notebooks and follow along. Okay, everyone, thanks for coming to this MLflow tutorial. We're going to be talking about standardizing the machine learning lifecycle using MLflow. This is actually a two-part tutorial, so part number one, this is really going to be a little bit more on the basic side, although hopefully there will be some stuff you haven't seen before. Part number two, we're going to get a little bit more into depth with an end-to-end productionization example. So my name's Shiviah. I'm a solutions architect with Databricks focusing on ML. And I work very closely with the MLflow team over in San Francisco. And my co-pilot over here is Michael Stelma. Michael, you want to introduce yourself?
Yeah. Hi, everybody. My name is Michael Stelma. I'm also a solution architect at Databricks and focusing also on the ML and ML-specific topics.
So for this two-part session, I'll be driving the first part, and Michael will be walking around and adding some details as needed. So if you run into a question while you're trying to work on stuff, throw your hand up and Michael can help you. For part number two, we're going to switch, and he's going to drive, and I'll be assisting. So what are we going to cover in this MLflow tutorial? So first thing I'm going to do is I'm going to give an discussion about what are the problems that MLflow is even trying to solve, and how exactly does MLflow solve it from a very high level. Then we're going to get into a practical example of how to actually run basic MLflow, basically how to get started in 60 seconds. Then I'll just spend a little bit of time talking about the basics of how MLflow can be useful for your team today. If your team is coming from, let's say, a scikit-learn version of the world, or just doing basic single node Python and data science. Then in part two, we're going to dive into how do you actually use MLflow in production? How have we used it internally in Databricks for our own analytics and some of the challenges we've run into, and some tips and tricks around that point. So to get started, why MLflow? What is the problem that MLflow is trying to solve? So people love talking about machine learning algorithms, and while they're super fun to discuss the various algorithms that come out, more often than not in production, the algorithms are a very small part of the total solution. Trying to actually get all the pipes to work, making sure that when you try out different algorithms, you're able to log your results and compare results from one experiment to another, and then actually serve those results in a reproducible manner. That turns out to be the difficulty. So this diagram is actually from a 2015 paper from Google at the NeurIPS, which is one of the foremost conferences for deep learning. Their whole point was even to get a basic logistic regression model into production for some of their web search, the ML code actually comprised a very small bit of the total architecture. So you can see a very small little square in the center that's green. That was the ML code. And everything else was actually the core of their infrastructure necessary to support that tiny little green bit. So where does this problem and this need for pipelines and architectures come from? Well, a lot of that complexity actually comes because when we're dealing with production data, we have lots of data living in the data engineering world, and we have tools associated with the data engineering world, databases and whatnot. And then when we get into the data science world, it's actually a completely different universe, various different tools, and these tools don't necessarily play nicely together. Furthermore, data engineers and data scientists don't really have much of a common language or a common culture to easily interface. So more often than not, what ends up happening is you get this silo. What this looks like in practice often is you'll have a data engineer working in Spark to prepare the data pipelines, and then at some point the data scientist might request a sample, so the data engineer will sample down a bit of the pipeline and pass it off to the data scientist, maybe as a CSV, and then maybe the data scientist will run Conda, she'll run some Python, maybe an XGBoost model here and there, and then finally she finds something somewhat decent. And she says, okay, great, we found a great model, let's put it into production. But she's not a machine learning engineer, so she needs someone else to do that. So now the question is, how do you actually get that machine learning model into production? Do you pickle it? Do you have to use some other format? Who do you pass it off to? How do they deploy it in a way that's reproducible and obeys the principles of continuous integration and continuous development? So then people say, well, maybe we can put this model in a Docker instance of some sort, we can deploy it that way. But at every step, the interface is actually the challenge in these deployment pipelines. The stuff at the very center of each workflow is actually pretty well understood. It's really the handoff that becomes the difficult part. So where we are today is that model deployment is really the wild, wild west. Even the top companies are still scratching their heads on different standardized ways to deploy models. I know this, in fact, because recently the MLflow team hired as their PM, the first PM for TensorFlow at Google, and he says, you know, Google's still trying to work out a lot of this stuff. So what people really need is a standard, and an open source standard at that. And that's where MLflow is basically supposed to come in. So we rolled MLflow out in last summer at the Spark Summit in San Francisco as an end-to-end machine learning lifecycle framework. It basically broke down into 3 parts: tracking, projects, and models. The idea here is, rather than focusing specifically on how you implement a model or the specific pipelines you're trying to implement, it was trying to look at the things that data science teams need to do again and again. First off is, when creating models, a data scientist doesn't know ahead of time which model is the correct one. There's actually a formal justification of this called the no free lunch theorem. So a priori, it just means you have to try out many, many models. But if you aren't having a consistent way of tracking these many models, then it becomes really hard to look back over all of your experiments and say, okay, this model was the best one, or maybe we should actually roll back to this other model. So MLflow tracking is a way to very easily allow data scientists to start tracking their models in a very simple and reproducible fashion. Once the data scientist has actually tracked their models quite a bit, maybe they find a good one and they want to pass that off to other data science teams, or maybe the ML engineering teams to experiment with and perhaps deploy. But the challenge there is that if the data science or machine learning teams that are receiving the model need to know the specific implementation of the model in order to actually run it, that is a huge cognitive load. So I don't want to know how to run the scikit-learn model versus TensorFlow model versus this handwritten model. I just want a single interface to be able to run it. So MLflow Projects introduced a lightweight YAML file to put in your GitHub repos that ensures a single interface for running machine learning projects that abstracts away whatever library you use for implementation. And then finally, MLflow Models does something very similar, except as a model wrapper. It was supposed to be a generic wrapper around various model types, and it also supported basically a Python class that you could roll your own wrapper around if you had a custom model, so to speak. So the result is that MLflow has been growing like crazy. A lot of people are using it. I actually think these numbers are slightly outdated. And in terms of growth, you can see the MLflow contributor growth on GitHub versus Apache Spark. So very exciting growth. So let's dive into the specifics. Experiment tracking. So the idea here is that, like I said before, we want a common and simple way for data science teams to track when they're experimenting. And that really breaks down into tracking parameters, metrics, so the inputs and the outputs to their experiments, as well as other artifacts like plots and data sets, and then models. One thing that I haven't really heard people talk about when discussing things on MLflow is the fact that this experimental tracking allows data scientists to work in different environments. So you may be working in RStudio, maybe your colleague's working in Jupyter, maybe someone else is just working on the command line in your HPC. But as long as everyone is tracking via MLflow and the MLflow is pointing to the same tracking server, that means that all these experiments are getting aggregated into one place. So like I said, tracking boils down into these 4 concepts, which are really just the inputs and the outputs, and then the various artifacts that go along with it. It also tracks some metadata, such as who ran it, at what point, and what was the source of the code. And if you're using Git in your repository, it will actually grab the Git hash. So I know this is going to be a little hard to see, but I'm going to actually show you a demo of what this looks like in a second. But one thing that you're going to see when working through the Databricks Community Edition is that when you run the tracking, you'll automatically see your results logged to a sidebar, and then there's a hosted tracking server. The one thing I want to point out about this is MLflow is completely open source. So if you want to run this on your own system or from the command line, you can do that. You just need to figure out how to host your own tracking server. If you run it on Community Edition or normal Databricks, it's already hosted for you. So let's just take a quick look at what tracking looks like in practice. Cool. So can everyone see that text okay? Yep, great. So one thing I've learned both as a data scientist in my previous life and working with data scientists now at Databricks is that data scientists are really stubborn when it comes to their workflow. If you've ever tried to get a data scientist off of Jupyter Hub or RStudio or whatever, it's a pain. But I've actually learned that there are 3 principles to getting data scientists to try out new things. Principle number 1, show them an improvement that is at least an order of magnitude. Principle number 2, show them how to get there in less than 60 seconds. And then principle number 3, show them how to do it in less than 3 steps. So what I found is if I can show you how to do something 10x better in less than 3 steps in less than 60 seconds, usually people switch. So going back to the MLflow tracking, if we look at how data scientists track today, one way is maybe they use a custom hand-rolled tracker that maybe everyone on the team aligned on, or maybe it's just someone who decided to roll their own. Maybe they aren't tracking anything. Maybe it's just print statements. Or maybe they're trying to use the engineering logging, but they're realizing, this was built for software engineering and not modeling. So the question is, how do we come up with a data science first logger that is native, simple, and gives you a 10x boost? So step number 1, you just import MLflow. It's a pip install in Python. Step number 2, I just grabbed an example from scikit-learn here. So this code, nothing special about the model in particular, but I'm going to specify where my logging will start with this with MLflow.startRun statement right here. Anything within the with statement will now be a candidate for logging. And then step number 3, I just decide on the parameters, the metrics, the models, and the artifacts I want to log via MLflow.logparams. Log metrics. Here I'm doing logging 2 models, and then if I wanted to, I can log some artifacts down here. That's it. Once you run this code, as I do right here, automatically we see that I actually logged a few different models, and if I go into a tracking server, which will take a second to load on Community Edition, you'll see that sure enough, these are now logged. So in this case, I only logged parameters, models, and artifacts, no metrics. But we can see the parameters were logged. Additionally, we have this example figure, which is showing up like so. And then when we logged the models, MLflow did something kind of interesting. Because it knew we were using scikit-learn, it pickled the model. And then it also inserted a conda YAML so that we know what the environment is necessary to reproduce it. And then looks like it didn't log an MLflow model for some reason. So in some cases, it will log a YAML file that specifies additional metadata if it thinks it's necessary. So in addition to logging the metrics parameters and artifacts, we also see that there's some metadata that was logged as well. Who ran it, what the source of the code was, when it was run, the duration, and then also this hash that it associates to run IDs. So for the first step, I'm going to just quickly give you a 5-second intro to how to get started on Community Edition, and then your first step is to go grab some code, whether it's from scikit-learn or something else, and just try logging, importing MLflow, logging some parameters and metrics. So if you've never been on Databricks before, step number 1 is go over to the Clusters tab and then create a cluster. On Community Edition, you can only create one at a time, so it's going to give me an error. So you'll just give it a cluster name, and at this point, select the 6.1 ML beta. This is a runtime that just comes prepackaged with a ton of machine learning libraries such as scikit-learn, XGBoost, Keras, et cetera, so you don't have to go through the work of installing that. So once you've selected that, you can just click Create Cluster. It will spin up a single node cluster, so not super interesting. Then, once you've created your cluster, go click on Home, create a notebook. You can give it whatever name you want. I'm very creative in my naming. And then if it doesn't automatically attach to that new cluster, you can just click here, and then there will be a button for clicking Attach. At this point, it's just like a Jupyter notebook. Run over here or Shift Enter. And then once that connects to the cluster, it will execute. So for the next few minutes, start up a cluster, create a notebook, import MLflow, and try starting a with MLflow experiment, log some metrics, see if they pop up on the sidebar, and then if you run into any issues, throw up your hand and Michael will help you. So we'll take a few minutes to do that. By the way, if you try and run the whole notebook as it currently is written, you're going to run into an error at the very bottom because I have some hard-coded run IDs. So in order to fix that, I was going to get to that later, but people are running into errors now. Once you go over to your run, you just have to take the run ID of your recent run and then substitute that in. This was from a previous run ID. Okay? So it seems like some people are moving ahead. I'm going to continue. Feel free to keep on working or listening in parallel. But there were a few other things I wanted to show with this notebook before we move on to projects and models. So we saw before that we were able to record some runs. In this case, we were just comparing two different models, nothing super fancy. This would be fully within the realm of the data scientist. The data scientist is trying out many different models. Maybe she's running some hyperparameter optimization, which actually Michael will show in the next section, to try out many, many different models. And then after doing a lot of experimentation, she might jump into the model tracking server in order to compare. But once you've actually found a decent model, the next question is how to actually reproduce that model. So in order to just reproduce it in Python, it's as simple as calling this thing called the MLflow PyFunc. So what we're going to do to reproduce that trained model that we had pickled in the first example is we go to the experiment run that we like. So I only did one in this case, not super interesting. And we just grab the hash associated with this run. And I just stick it in here. Furthermore, the path to the model is just simply the name of the directory that the model I want to run is located in. So we see here I set the path to first fitted model. And then by using mlflow.sklearn.load model and then adding in the appropriate model URI, I'm able to reload the model. This is really nice because, of course, we've implicitly been using MLflow models here. It doesn't matter if it's scikit-learn or Keras or something else. This is a generic wrapper around many different libraries. So the interface to reloading serialized models is the same. I don't need to know at this point that this model is actually one version or another. I'm kind of cheating a little bit here because I did have MLflow sklearn. But in general, that's not the case. So this is a very nice normal Python model. If I want my colleague to be able to reproduce it, they can use this. But we can actually do something a little bit even more interesting, which is actually on the deployment side. So let's say a lot of data scientists, they spend time building models, but they have a really hard time getting the rest of the organization to use their models. Maybe it's hard to get engineering to use it, but even more difficult is the question of how do we get the business analyst to use our models? Because even though REST APIs are sexy, for many enterprise, SQL is actually the core API. So let's say we wanted to take our model that we just created and actually enable some business analysts who just know SQL to actually use it. Well, instead of using the scikit-learn load model, we're going to use something called the Spark user-defined function. So what this will do is this will load our MLflow single node Python model into a Spark user-defined function. So now it can be used in distributed mode. And sure enough, we see once we load this, now we can actually take a Spark data frame and run it across Spark, which is great because now you have a way to take your model and run it in every Spark language like R, Python, Scala, and SQL. But actually to get to the SQL step, there's one additional step, which is we actually have to do spark.udf.register. So once we have this final step completed and we have a Spark table which we can run SQL against, we can now actually say something like select model. In this case, I just did a single random column of inputs. That's why it has a 0. But if you had named columns, you'd substitute in your named columns, of course. But here I'm able to take my model and actually register it as a generic SQL function that's now running distributed on Spark. And because this is Spark, it runs both in batch and structured streaming. So this is a very nice way to take your models and then actually run them structured streaming on, let's say, a Delta table. So now that business analyst, they don't need to know how to run a Keras model. They can just register it. You can just have it registered to a SQL function, and then they can use that as a drop-in. This is something that I found very, very clean and unlocks a lot of potential. Now, there's a few things, a few caveats here that I should just call out. Because our original model is a single node model, not a distributed model, that means that when we're running it, the input needs to be able to fit on a single node, right? So the stuff that the model is taking in needs to be small. For many models that are just training or just serving up a single row prediction, this is not an issue. But if the input to your model is, let's say, a massive amount of text, then this won't work. Other things is that even though we're in Spark, Spark is essentially treating this Python model as a black box. So the performance isn't always going to be as great as if you're using a native Spark machine learning model or a native Spark function. So this becomes very valuable in the cases where you don't need near real-time results. It will take a little bit longer, but not too bad. I mean, in this case, it took about 2.6 seconds, and the data frame I created was okay. The data frame was pretty small. So just to give you an idea about the relative performance. But again, we're not doing this for performance reasons. We're doing this as a way for data science teams to enable the larger organization to use their models using MLflow.
I guess you can have also the whole data transformation in the pipeline and everything that's run at once?
So the question was, can you have the whole data transformation into the pipeline and then just run it all at once as a SQL function, right? Again, you can do that. You're going to experience a little bit of a hit on the performance side by using native Python stuff. So if things tend to get slow, then you want to move as much as you can back into native Spark. But I'm going to show you in the second bit of this talk actually a way that you can blend the two that's very performant. So next, I'm just going to quickly talk about the projects and the models. So we already saw the MLflow models implicitly. But for reproducible projects, the idea is how can you have a project that, again, you don't need to know the specific way it's implemented. It has a generic interface that allows people to easily run it both locally and on remote. The secret to this is MLflow introduces this lightweight YAML script called an MLflow project file that specifies the entry points as well as the environment necessary to construct your code. Once you fully specify this, you can then just specify MLflow run and then point to the GitHub repo or Git repo for your project. And then that will create and build your environments from scratch and execute your code. So furthermore, this will construct it locally, but if you wanted to actually run it remote, you can also, if you have a Databricks account, do something like -b and then point to the Databricks URL with the optional JSON file specifying your cluster. So this turns out to be super nice because data scientists often are used to working locally, and maybe they don't want to switch everything off to a remote cluster. But for deployment, you probably should be not using your laptop. So having a way to switch back and forth in basically a single line of code between remote clusters and your local environment turns out to be very clean. Okay, and then finally, model deployment. So we talked about one version of model deployment using Spark user-defined functions. There's a lot of other flavors of model deployment. Model deployment largely falls into 3 buckets. So bucket number 1 is where someone treats their trained model as basically a library, and you just import it and then use it directly within your code. So that's kind of what we were doing when we had our PyFunc, if you remember. Version number 2 is actually where you treat your model as an API that people can hit. So a lot of the big players like SageMaker and Azure ML are going down this route. It has the challenges of sometimes it can be quite slow to hit a model again and again, and also the model is often remote, which means that your code needs to dial home somehow. And then the third, which I don't think people talk about nearly enough, is that you can actually just pre-register your results as a table and treat it as a lookup table. More often than not, if you don't have a need for immediate results or you think the results can be pre-calculated, having a lookup table of results to hit tends to be actually very simple for your architecture. But in the case of hitting an API, We have ways via MLflow to basically package stuff up and ship it off as a Docker instance. It also interfaces with Azure ML and SageMaker as well. So once you actually save that model, if depending on what model you're using, in this case TensorFlow, that ML model file will be generated. It will show the hash unique to your run ID, as well as some other stuff about what the signatures are necessary to call it when you use something like MLflow serve. So again, there's various ways to do this. Hooking into REST, you can look at our documentation for that, depending on if you're using SageMaker, Docker, or Azure ML. OK, so I'm going to quickly switch over to what I think is a super unique and interesting use case for MLflow that I haven't heard too many people talk about. So going back to these user-defined functions as a way to interface single-node Python back into Spark, one thing that people noticed when trying to register single-node Python functions into Spark initially is that the performance was just so bad. Really, really, really bad. Has anyone actually experienced super bad Spark UDF performance? OK, only 2 people. The rest have been spared. A big reason for this is that when you register that Python function as a Spark function, Spark has no idea how it works. It's essentially a black box. And so when it was applying that function to columns, it had to do that element by element. And if you recall your basic CS data structures class, this equals very, very bad performance. What would be much better is if we had a way to actually vectorize a column, so we could basically run all the calculations in constant time instead of linear time lookups. So Databricks worked with Hadley Wickham and Wes McKinney, who were the creators of the dplyr and pandas in R and Python respectively, to integrate a new file format called Apache Arrow into Spark and Databricks. So Apache Arrow is one step above your standard CSV or JSON in that it's actually a compressed columnar storage. Now, if you've ever worked with Parquet in Spark, that should sound really familiar. And it should, because Parquet Arrow is essentially, or Apache Arrow is essentially the single node version of a Parquet. What this means in practice is that it becomes very easy to interchange distributed Parquet formats back into Apache Arrow on the single node, run hyper-optimized Python and R against the Apache Arrow, and then translate those back into Parquet for a seamless Spark to Python to Spark interface. So the result of this was what was called the pandas UDFs. And we actually had a great blog post about it a while back. Where, among other things, people showed that you could actually use it for pandas transformations of columns that were taking super slow. You would just wrap it in an @pandas UDF decorator, and then it became something you could run in Spark. But something that they didn't really spend much time on, this virtual summit thing's super annoying, is the idea that you could actually apply pandas UDFs not just to columnar transformations, but actually to data frame transformations. And that turned out to be an incredibly powerful idea. So I wanted to show you how this could actually work. The idea is as follows. Usually when data scientists hear about Spark, they're like, oh my gosh, I'm going to have to rewrite all of my Python code into Spark and use Spark ML. Like, Spark ML kind of sucks compared to my single node Python models. Why do I want to do, I don't want to do this, right? But that's a huge mistake. It turns out you can actually use your single node Python models completely with Spark without having to rewrite much of anything. And again, going back to my 3 rules for convincing data scientists to do anything, got to show 10x the value in 60 seconds or less, and in 3 steps or less. So let's see how we do that in the distributed model sense using MLflow and pandas UDF. So what I want to do essentially is I have a single node model. that I'm using some MLflow in. This model isn't super interesting. It's just taking some averages. So nothing super fancy here. But let's just pretend it's an interesting model. Now, my challenge is my data has many, many different IDs that I've partitioned over. Let's say, for instance, this is a forecasting problem, and I want to do a forecast for every product SKU I have. This is actually a real internal use case we use at Databricks. And a lot of major retailers and some oil and gas companies have implemented something similar. So I have, let's say, tens of thousands or 100,000 different product SKUs, and each one needs its own forecast. Now, if I'm a single node person, I know that each forecast by itself isn't that much data. Maybe it's only 2 years worth of history, and we only take daily or hourly measurements. So this is very well within the realm of single node data science. However, in aggregate, 100,000 of those becomes really challenging. Do I implement that as just a really nasty for loop? What do I do? Do I try and do a apply of some sort in using R? People really, really struggle with this, and more often than not, they'll run something. 5 hours later, their laptop will burn out. So how do we take this thing with some partition ID and distribute it in 3 steps or less? So first off, just a little explanation of what this data actually looks like. So I just generated 2 random distributions. I have a uniform distribution and a normal distribution. And I also added a partition ID, which just does modulo 10 on the end. So we have 0 through 9 for our partition ID. And we're going to use that to make 10 different model results, essentially. OK. So here's where we get into the sexy bits. In order to distribute this function, I'm going to take my single node thing. I'm going to nest it with MLflow.startRun so I can track all of those distributed models, and I'm going to wrap it in an @pandas UDF. Now, I've hidden some magic in here, which I'll explain in a second, but this is really the crux. The key is that you can take that pandas UDF, and using this grouped map type, this allows you to take those single node Python models and turn it into distributed code. We can check that our pandas UDF, our distributed UDF, actually works in the single node version just by doing a .func and calling it on a pandas data frame. So in this case, it returns the average of our various distributions. Now, in order to actually run it on a full Spark data frame, we group by our partition ID, and we apply the model. This will then generate, for each partition, a model result. And then furthermore, we have over here that this was automatically logging a bunch of parameters. It's kind of scrolling off the screen. But you can see for each parameter, there's a log. Now, again, going back to the idea that maybe we have 10,000 different SKUs, what that means is you come up with a single node data science model using scikit-learn, XGBoost, whatever you want. You make sure it works on one SKU. Then you register that as a pandas UDF. You say group by SKU ID, apply model. You have your MLflow code in there. Boom. Maybe 20 minutes later, you can look through all of your MLflow results and then automatically just go through all the 10,000 SKUs, just like that. That's actually how we're using it internally. Or let's say you're trying to do hyperparameter optimization. Instead of having to run each hyperparameter optimization step in serial, you can actually just map all of the hyperparameters to essentially partitions and say, run a model against each of these hyperparameter partitions. Do it simultaneously, right? We're talking about horizontally scaling instead of scaling out across time. And MLflow combined with pandas UDFs actually allows you to do that. OK, so where was some of the magic that I hid? Because I know we're almost out of time, and I did hide some magic that I want to tell you about. So point number 1. This thing has to require a Spark schema. So what's going on here is it's taking your Parquet, it's converting it to Apache Arrow, running some pandas native code on the Apache Arrow, and then that Apache Arrow needs to convert back to Parquet. But in order to do that, you need to specify a Parquet schema. How did I get that Parquet schema? Well, because I was lazy, I just ran the single node result, and then I turned it into a Spark data frame and grabbed the schema that way. So that's very simple. For production jobs, you always want to write your schema explicitly up front and hard code it rather than having some dynamic schema generation like this. Second of all, I had this little bit here saying start run experiment ID equals experiment ID. There is some magic there. So whenever you start a Databricks notebook, because MLflow is natively integrated, it automatically creates an experiment in MLflow associated with each notebook. And in order for MLflow to correctly distribute over all of the worker nodes, you need to specify where it's going to phone the results back to, which server. So what we're actually doing here is we're actually doing a little trick to grab the experiment ID. But if you look at this code and you're like, man, I'm never going to remember that, the really easy way to actually remember it is just go into your MLflow tracking server. And right here, this is going to be the experiment ID. So you can hard code that in if you want. So those are basically the two tricks. You need to point to which experiment MLflow is going to send your results when you distribute it over your Spark cluster. And then also you need to come up with a schema. I will warn you, when distributing Python code, debugging becomes a lot more difficult because now you're having to go through the Spark debugger, not just the native Python debugger. So it is a bit more challenging. But internally, I'll tell you, when we first started doing some various forecasting exercises, our data science team was running into an issue where they were, after about 4 hours, getting an out-of-memory error trying to do a gapply in R. When we switched out the pandas UDFs, the whole thing ran in less than 15 minutes on over 10,000 accounts. So that's the sort of change that you can get out of this pattern. MLflow brings it all together with the tracking. And with that, I think we're out of time. So in a bit, we're going to be doing part 2, where we're going to be diving deeper into productionization with ML. In the meantime, I'll be out in the hallway doing an MLflow Ask Me Anything, where you can come and chat with me and some other MLflow users. Thank you very much.